Okay, hi everyone. I hope this video finds you well. So today we are going to talk about learning to program, why and how, and more background information. So after today's lecture, you will be knowing what we are going to talk about during the quarter and what you should be learning. Let's start with this question. What did we learn about so far? So we learned about understanding the parts of the computer, doing the hello world, and getting to know the build process and the loading process. So the build process and what each of these parts mean. So this is a file, another file, and eventually we will get a file on the hard drive. This is a file that is previously created, and those both are processes, right? So your code is being checked for errors, then converted to machine code. Then the machine code is being combined, linked with previously created code libraries to eventually create an executable file that will be stored on the disk. So why is programming hard to learn for most people? Now, the answer to that is the context. So you need to build context, a mental map, to form a deep understanding. For most people taking this course, unlike other subjects, you have none or very little context. So think about learning to code like learning to read. You learn the letters before you try to learn to read. So we will learn about the parts of programming before we learn how to put them together to create a masterpiece, your code. So the learning pyramid. There are two main categories of teaching methods: passive and participatory. Now, in the passive teaching methods, you get pretty much like 5% after getting the lecture, 10% after reading the slides and watching the lecture, 20% from audio or visual, 30% of demonstration if someone did a project and demonstrated that in front of you. But with the participatory teaching methods, you get about 50% if you were in a group discussion, 75% if you practiced, and if you become a teacher of that subject, you will understand up to 90%. Or if you do some research also and do these things, you would get to understanding more and more. So the Bloom's taxonomy, you start with recognizing and recalling facts, which is the remember phase. Then you get to understanding what the facts mean, the understand phase. Then applying the facts, the rules, the concepts, and the ideas. This is where you apply. Breaking down information into components part, analysis, judging the value of information or idea, evaluation, and eventually creation, combining parts to make a new whole. So why should I learn program? From financial point of view, currently the computing jobs are on the rise, and we have way more jobs than we have graduates. So it's a good field to be in, right? And it's rewarding, as you can see. So the national average mid-career computing and computer science salary is 110K, and that was in the projection done for 2014 to 2024 period. So about Fred Brooks. Now, I'm not going to say who is Fred Brooks. I'm going to leave that for you to get some bonus points. So on Canvas, go to this assignment page of who is Fred Brooks and explain, write a brief essay in about 10 lines. So Fred Brooks says why he loves programming. He says one reason is the sheer joy of making things. The second, the pleasure of making things that are useful to other people. It's like you're serving the community, right? Participating in a solution to a problem the community faces. Also, the fascination of fashioning complex puzzle-like objects of interlocking moving parts. The joy of always learning, and the delight of working in a tractable medium. A tractable medium. So Alan Turing, another bonus question is who is Alan Turing? I'll leave that to you. You can explain that also in about 10 lines. If we are in face-to-face class, I would ask one volunteer to explain it to the whole class. But since we are in online class now, you must explain it in a brief essay to get bonus points if you want that. So Alan Turing invented the Turing machine. Alan Turing is very smart, guys, but we are not going to talk about Alan Turing. I'll leave that to you. We are going to talk about the Turing machine. The Turing machine is a hypothetical device that manipulates symbols on strip of tape according to a table of rules. Despite its simplicity, a Turing machine can be adapted to simulate the logic of any computer algorithm and is particularly useful in explaining the functions of a CPU inside a computer. So briefly, the Turing machine, suppose that there is a tape where you have zeros and ones in syllables, and there is a tip of the machine that reads and writes. This is the head, and when you read a bit, 0 or 1, you go to action table to see if that 0 was in that exact place. What does that mean? Then after you know the meaning, you do change the state register and then write. You do the write. Now you either change that to 1 and move to another position, or keep that as a 0 and move to another position, and so on with each bit. So a program is a machine. Another way to view this is that a program is a machine. This machine is comprised of many parts. If you attempted to put together a machine without knowing much about its parts, it would be very difficult and very confusing, right? So also you can look at programs as abstract. So what is basically abstract reasoning? Abstract reasoning refers to the ability to analyze information, detect patterns and relationships, and solve problems on a complex level, an intangible level. So abstract reasoning skills include being able to formulate theories about the nature of objects and ideas. So, for example, if we are going from North Bay to Kitchener, what is the best way? Now, you may ask yourself, the best way or the shortest way? Now, the best way is not necessarily the shortest way. The best way, the one with least bumps, and when you talk about shortest, You may consider shortest in time or shortest in distance. This is why you should have representation. The representation helps you understand the problem and can remove unnecessary information. We can manipulate the model to get some solution. The shortest path example is explained in this link. It's called the Dijkstra algorithm, or some people call it Dijkstra algorithm. So basic abstractions of programming. We have conditionals, we have loops, we have variables, and we have sequences. Now we are going to talk about each one of these briefly, because we are going to dig deep into each one of them during the whole quarter. So pretty much each one of these would take at least a week. So the Boolean logic, here's another bonus opportunity. Who came up with the idea of a Boolean logic? So write a brief essay on who came up with the Boolean logic on the Canvas assignment page. So the Boolean logic uses the values of true and false to make decisions on their own or through combinations. So either just true or false, or combination of those. So it's like when you decide, we said to make decisions, right? So when you decide to go to Starbucks or not, basically you would ask yourself some questions. For example, one of them is, if I have $3, then I can get a drip coffee at Starbucks, right? But if you don't have money, you won't go to Starbucks. So you made a decision, and the result of that was, first, either true or false. Do you have a $3? Now, if yes, you can go to Starbucks. If not, then you don't go to Starbucks. So here is another example of Boolean expressions. Sheep. So these sheep are trying to get to the grass. So the first door is open. The second door is open, or let's just say left gate and right gate. Left gate is open, which represented by true. Right gate is open, represented also by true. Then the ability to get to the grass is true, right? Because they can get to the grass. If one of them is closed, for example, the right one is closed, which will be represented by false, and the other is open, true, then this still can get to the grass. So the final result is true. The ability to get to the grass is true. Left gate is closed, but the right gate is open. They still can get to the class, which is represented by true. The ability to get to the grass is true. Now, if both were closed, then the ability to get to the grass is false. Now, which one do you think? Which scenario? Is it the logical and or logical or? Is it and decision or an or decision? Now, basically, this is the or decision. This is the or decision. If any of these, or in other words, if left gate is open or the right gate is open, sheep can get to the grass. So let's talk about variables. Variables keep track of information. And we talked about them last lecture. We said variables are storage. Or the definition of variables, basically named memory location. Memory location represents storage, and the name is needed because we want to use that name, or we want to associate that memory location with a name that is easily remembered. So there are two kinds of variables: data storage variables and reference storage variables. So what we are going to use in this quarter is data storage variables. Next quarter in CS 131, you get to use reference storage variables. So Simply data storage, those are storing data like 1, 2, 3. Those are storing memory addresses. So variables have two operations. Overwrite the data stored if I want to change the data stored. So x points to 3, then I delete 3 and put 5. I overwritten 3 with 5. Retrieve if I want to read the content of x. I read it as 5. So value storage variables, basically these are the data storage variables. C++ requires the type when creating a data storage variable. Now, these are called built-in types. So these types are called built-in types. There are limited number of legal types for data storage variables. For example, bool. Bool is a data type that allows you to store true or false values. Int, integer. This integer data type, int, is abbreviation of integer, and this allows you to store integers. When I say integers, whole number, whole numbers, like -2, -15, 0, 15, 1 million, and so on. So conditionals. Conditionals used to make choice, to make a decision. So should I go left or right? Now, based on the circumstances, a program can make a decision. For example, if I'm approaching a red light in my car, if the light is red, I slow down. So in computer programming, the state might be a variable red light true. Now, if it's not a red light, if it's green or yellow, then red light would be false. Then I keep going. True, stop. Right? Red light is true, then stop. So I check a condition. I check a condition. And if it's true, I evaluate part of code. For example, starting the sequence to stop the car. If it's false, then skip that sequence and do not stop the car and keep going. Loops, used to repeat a sequence of code. Now, for example, if I have a stack of 25 exams for 25 students, for each exam, I would grade question 1, question 2, question 3, then total the points, and then record the score. So if a condition is true, now what is that condition? If I still have exams, I graded the first one, then I check, do I have any exams left? Yes. Okay. Do the sequence, and this is the sequence, right? Then go to ask back. Okay, check the condition. Do I have any exams left? Yes, keep doing the sequence again, over and over again, until I run out of all exams. Then, is there any exams left? No, then okay, go out. Don't do the sequence, skip the sequence, and go out of the loop. Now, a sequence is important because the order of actions in the sequence matters. I cannot record the score before grading the first question, the second question, the third, and then totaling the points. So I have to go through grading the first question, then the second, then the third, then totaling the points to get a score to store, right? Now we have something called callable units. For each exam, I have this sequence, right? I can group these actions together to create a function. A function is a callable unit. A callable unit. We can call that function. So, for example, I'm just going to call that grading sequence. And I'm going to put this sequence in here. Then whenever I want to grade an exam, I just call it by the name grading sequence, and it's going to call that execute these sequentially, starting from grading question 1, 2, 3, then total point, then eventually record the score. So this allows reuse of code and several other advantages. We are going to talk about these advantages when we get to the callable units. We are going to spend half a week on just callable units. So what does it mean to be digital? Now, digital usually refers to something using digits, particularly binary digits, zeros and ones. Often refers to anything that can only have two possible values. So digital data is the data that is stored in binary. Digital devices are devices that work with binary data. Computers are digital devices, so they work with binary data. So programming languages. We have machine languages, sequences of zeros and ones, as simple as that. Assembly languages using short words known as mnemonics to write programs. And those mnemonics must be translated by assembler and still considered low-level language. Some people consider that as mid-level languages. Then we have high-level languages like C++, the one we are learning. Now, more human-readable languages that allow programmers to create programs without knowing how CPU works. So, modern languages are mostly high-level languages. So, keywords, operators, and syntax. High-level languages use keywords that have special meaning and cannot be used for any purpose other than to write programs like bool in C++ or int. This is to create a variable of type bool that can store true or false values, right? Int to store numbers, a data type that allows you to store numbers, whole numbers. Operators are keywords that represent special program functions such as addition, subtraction, multiplication, modulus, and so on. Syntax is a set of rules that must be strictly followed to write computer understandable instructions. Syntax errors is a mistake or a violation of these rules. Remember, we checked syntax error, the grammar and the spelling and these rules in our code. Each instruction in a program is called a statement. In C++, each statement ends with a semicolon. So compilers versus interpreters. A compiler translates high-level language program to separate machine program for a CPU to read and execute. So a source code is containing the statements a programmer writes in high-level language. Compilation is the translation of a text-based source code to binary codes. Interpreter, however, reads, translates, and executes the instruction of a high-level language. Some examples of interpreted languages are PHP, Perl, Python, and ASP.NET. So, in compilation, a source code goes through a process to eventually create executable code, and this executable code is going to be in a machine language to eventually load it to be used by the machine. A source code in interpreted languages is converted to intermediate code so that the interpreter reads, translate, and execute. Reads, translate, and execute. These are three important steps in the interpreted languages. So, compilers and interpreters. The compiled languages like C, C++, Objective-C, COBOL, and many others. Interpreted languages, however, like JavaScript, Python, Lisp, Scheme, and many others. So the difference between compiled languages and interpreted languages, compiled languages are faster and type safety. Type safety, they check the type before they run the program, or in other words, at compilation time, which we call static typing. Interpreted languages use dynamic typing, checking the type of the variable on the fly when it's being defined. Remember? Read, translate, then execute line by line. And in the notes of this slide, I left you explanation of reflection versus reflective. So I'm just going to show you that quickly. Here it is. Reflective versus reflection. So the main reason we have interpreted languages because we want them to be platform independent. You run them on any platform. The executable file coming out of the interpreted languages run on any platform is going to work. However, in compiled languages, not every platform is going to be able to run your code. For example, in the C++ language we are learning, the .exe executable file, the product of the compilation process, can be run on Windows. However, it cannot be running on a Mac. You cannot take that exe and put it in Mac and run it. You need to take the code and then compile it on a Mac device, then run it as executable file, but not with the exe extension, right? So compilers and interpreter. Some languages like C# and Java combines the two processes, the compilation first, then the interpretation. First the compilation, then the interpretation. But this is not as fast as compiled languages. So always think about the build process and what each part is doing. This is the compilation process or the build process in C++, what we call the build process. Here is another look. File, this is a process, it goes into the compilation process to produce object file to be linked with previous or existing code to eventually create executable file. So general performance comparison. Which one is faster? So the GNU C, old C, is very fast, about the same speed, about the same execution time is the same code in C++ or in Microsoft Visual C 2005. Python is using ranges. We have Python 2.6, 2.7, 3.6, so it's a little bit different, but it's not as fast as C or C++. So here's programming languages out there, and what is important to us is TOB index, the importance of being earnest. So as you can see, Java is used by custom applications for businesses or to create custom applications for businesses. It's taken about 19% of the programming languages used. C is 16%, C++ 9%, and so on. So why do computers use binary? Because computer could have been built to work even with decimal numbers, but the use of binary is coming from engineering point of view. It's basically a lot less likely there will be an error if there are only two states to distinguish. It's about voltage, right? The presence of a voltage above a certain threshold is going to be 1 or true. The absence of voltage under a specific threshold is going to be false or zero. So electricity or not. So binary, any number in decimal can be represented by binary. Now the way to represent that is to have 1, 2, 4, 8, and then 16 if you want, 32. Always time this number by 2, 64 times 2, 128 times 2, 256, and so on. So if you want, for example, to have 11, what kind of combination you can get 11 from? So 8, 2, and 1. So 1, for each number I circled, you get 1. Anything I didn't circle, you represent that with 0. So 1, 0, 1, 1. This is 11. 12 is 8, 4, 0, 0. So 1, 1, 0, 0. And so on. And so on. So if computers use binary and source code is text, how it is stored? How is it stored? So all data stored in computer is converted to a sequence of zeros and ones. Each piece is called a bit. So every 0 and 1 is called a bit. So a bit could be either 0 or 1. Now a computer's memory is divided into a tiny storage locations called bytes. 8 bytes makes 8 bits makes a byte. A combination of bits, zeros and ones, are used to represent a character. For example, the character uppercase A is represented by 65 in the ASCII code, and we are going to talk about ASCII code in a little bit. But 65 is represented by 1, 0, 0, 0, 0, 0, 1. So in the memory you will find 1, 0, 0, 0, 1, and when you print that memory location, it's going to represent that as A on your console. There is a process to convert that back to A. So the ASCII. So the ASCII table is consisting of all characters, operations like interrupting signals, deletion, shift in, shift out, all special characters, space, alphabets, whether it's in uppercase or lowercase. So ASCII code is storing all these, and the ASCII code is 128 characters. English alphabets and the special characters, including the digits. So 0 as a character or a digit is represented by 48 in ASCII. Now 48 is going to be converted to binary to be stored in the memory. When you call it back, the 48 or the binary representation of the 48 is going to be converted to a 0 so that displayed on your console. So originally based on English alphabet, ASCII encodes 128 specified characters into a 7-bit integer as shown by the ASCII chart in the previous slide, right? The characters encoded are numbers 0 to 9, lowercase letters A to Z, uppercase letters A to Z, basic punctuation symbols, control codes that originated with a tilde type machines, and a space. Again, for example, lowercase j would be a binary 1101010 and a decimal 106. So usually I would ask you to memorize only two things: the uppercase A representation in decimal and the lowercase a representation in decimal. So the uppercase A is 65. The lowercase a is 97. So if I would ask you what is C in lowercase c in decimal or in ASCII, you would say it's 99 because you would add 2 to that. So plus 2, you would get the C, right? A, B, C, 97, 98, 99. So the Unicode, because we don't have only the English language in the world, we have many, many languages. The Unicode is a superset of ASCII. It includes the first 0 to 128 or the first 128 with the same meaning, all of them. The numbers, the English alphabets, lowercase and uppercase, the control code and the space. But then we added a lot more. So Unicode is computing industry standard for the consistent encoding, representation, and handling of text expressed in most of the world's writing systems. So it's developed in conjunction with the Universal Coded Character Set (UCS) standard and published as the Unicode standard. The latest version of Unicode contains a repertoire of more than 128,000. So basically this is being represented by 16-bit, which can store up to 65,000, more than 65,000 actually. So it's going to contain representation to all alphabets, to all numbers in all languages. It's covering more than 135 modern and historic scripts, as well as multiple symbol sets like Greek, Arabic, Hangul, anything you can think of. Anything you can think of. So that's it for today. See you in the next one.